Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to work the question shifted search. And this is really a deep dive into binary search. We're going to see how to implement it from scratch, and also how to modify it to handle a problem's constraints. So the question says you're given a shifted array of sorted integers. So an unshifted array means all the items increase from beginning to end, so they're ordered in ascending order, they're sorted. Here, our items were sorted, but then they've been shifted by an unknown number of units. So instead of 0, 1, 2 being at the beginning, we now see that it's at the end. So 3 through 9 are increasing, then we have this change point, and then 0 through 2 are increasing. And what you want to do is find a target value in this shifted array, and then return the index of that target value. So here we have the target of 5, we see that it's in index 2, so the answer is 2. And one thing that's important to note is all these items are unique. So it could get a little more complex if we have duplicate items. This constraint is just telling you there are no duplicates. You can only consider that an item will appear one time. And you can focus on the logic of implementing the search. Also, an item may not exist in the array. If the item doesn't exist, our target can't be found, then we just return -1 as the solution. So typically when we have a sorted array, we use binary search. Here we see an array sorted from 0 to 9, and if we want to find the target 6, we would use binary search to find that in log n time. So we put a pointer at the first item, a pointer at the last item, and we find the midpoint between these two items. Then we compare our target with the current midpoint. Since it's sorted, if the target is larger, then we know we move right in the array. If it's smaller, we would move left. In this case, 6 is larger than 4, so we move right. Now we've gotten rid of half the items. We know our target is not in that left half. What we do then is update our start to the first item that hasn't been considered. In this case, it's 5. Our end hasn't shifted, and it's still on 9, and now we find the midpoint of 7. We check our target against this value now. We see that 6 is less than 7, so we moved left. So each time for a normal binary search, you're cutting out half the array and moving in one direction or the other based on the midpoint. So normal binary search is simple. We only have to make a comparison of the midpoint to the target. And since the array is sorted, we know that if the midpoint is larger than the target, then the target must be to the left of the midpoint. If the midpoint is smaller than the target, well, that must mean the target is to the right of the midpoint. And then as we hone in our array, we just keep checking it against each new midpoint until we find the value. Since our array has been shifted though, it's not going to be quite that easy to solve it. We can't just use a standard binary search. For example, in this first question, if we were looking for 0, well, we would find our midpoint between the start and the end and say 7's greater than 0, so typically we would look left. But because it's been shifted, it's moved the 0 to the right half. So now we're going to have to see what we know about these arrays to be able to solve it and still use our binary search. We can see that this shift point can occur in either half. So based on our midpoint, it can be in the right, where you have the largest value and the smallest value touching, or it can be in the left, where you still have that largest value and smallest value touching. But that means the other half is still ascending correctly. 3 through 7 is still ordered. Below, 1 through 6 is still ordered. The only issue is one of the halves is not ordered. So here, it goes 7, 8, 9, then flips to 0, then 1. And then above, you have 7, 8, 9, then it flips, then it goes 0, 1, 2. So one of these halves is still ascending correctly, but the other half has that flip in it, has that rotation point that causes the numbers to no longer be ordered correctly. So the key to this question is understanding that correctly ordered half. In normal binary search, we compare the midpoint to the target, but now we're going to compare the midpoint to a range of halves. So since this is 3 through 7 ordered correctly, well, if we're saying looking for the target 9, well, we know 9 is not between 3 and 7, so it must be to the right. Then if we look below, we see that the left half is not ordered correctly, so the right half must be ordered correctly. We compare 9 to this range, 1 through 6, it's not in this range, so it must be to the left. And this is true if the number is larger or smaller. We check, let's say 0 this time. 0 is not between 3 and 7, it's smaller, so it must be in the right half. And again, we check, okay, this is not ordered correctly, the right half is ordered correctly. 0 is not between 1 and 6, so it must be in the left half. So we don't care if the target is larger or smaller than the range of correctly ordered values, we just know it's not in that range. And that must mean it's in the other half. So how do we know which half is ordered correctly? Well, all we have to do is check the start with the midpoint. If our start is less than the midpoint, it means they're all ascending. In this case, we see the start is larger than the midpoint, so there must be this rotation. So we can determine the correctly ordered half just by comparing the start and the midpoint, and then we compare our target to the range that is ordered correctly to know which direction to move. And it doesn't matter if our number is larger or smaller, all we care that if it's outside the range, it must be in the other half. So let's look at the possible cases. We see that the mid is greater than the start. This must mean that all the items in the left half are ascending correctly, so our rotation point must be in the right half. So we'll use the left to determine where our target is located. We see that 6 is greater than 3 and less than 7, so it must be in this correctly sorted range, so we would move left. We would move our endpoint to the current mid, and then we would check between those two values. Now let's take a target that's not in the correctly ordered half. Left is correctly ordered. We see 1 is not between 3 and 7, so we know that we need to go to the right half. Then we update our points and we move the start to where the midpoint is now. The other case is that the midpoint is less than the starting value. This means we had that rotation and that at some point we had the largest value, flip, and then start over with the smallest value. This means the right half is correctly ordered. So when we compare our target, we see that 4 is between 1 and 6, so it must be in this right half. Now let's take a target of 0. Well, 0 is not between 1 and 6, so it must be in the left half. So we can very easily determine which half is ordered correctly, and then we compare our target to that range to know which half the item must be in, whether it's greater or smaller than the range of values. Or if it's inside that range, then we know it must be inside that correctly ordered half. So now we have our logic. Let's walk through a full example. We're looking for the target 0 in this shifted array below. We start by finding the start and endpoint and then get the mid between those. Next, we want to check which half is correctly ordered. We see that the start is greater than the mid, so we know that the rotation must occur between these two values, so the right half must be correctly ordered. We check if our target is between the mid and the end. It's not, so we go left. We've eliminated half of the array already. We know that 0 cannot be in between those values, so we move left. We keep our start the same, and we update our endpoint to be the first value that hasn't been checked in that other half. We find the midpoint between the start and the new end, and now we check which half is ordered correctly. We see that the start is less than mid, so these values must be in the correct order. So we check if 0 is between 7 and 8. It's not, so we know we need to move right. We have eliminated half of the remaining array. Now our start and the mid are the same values. We're really starting to converge now. We see that start is equal to mid, but it really doesn't have as much meaning. We just know that we can check the target against this value. 0 is not between 9 and 9, so we must move right. Our midpoint is equal to the target. We've converged, we're out of values, and we found the answer. Our index is 3 for the target of 0. So now let's just talk through all the steps of the solution. You find your start and endpoint, and then you find the mid between those. Then you need to determine which half is ordered correctly to make the comparison for your target. Using this correctly ordered half, you determine if the target is within the range or not. If it is within the range, then you update your values to then consider that correctly ordered half. Otherwise, you know it's in the incorrectly ordered half, so you update them to the other side. You continue looping and updating these halves until your points converge or you find the target value. The big O of this is still log n time. We're still doing a binary search and we're eliminating half the values each iteration, so it's very fast. We're also not adding any additional data structures, so it's O of 1 constant space. And now we're ready to implement our solution function, find target index. And this function takes an array of items, which are shifted, ordered items, and we're looking for a target. And when we find the target, we return that target's index, and if we can't find the target, we return -1. We know we're doing a modified version of binary search, so that means we need the start index, which is just the first item initially, and the end index, which is just the last item initially. When we iterate in a binary search, we use a while loop. And we do this because we don't know when the items will converge, but once that start index reaches the end index, that means we've checked all the items. So while start index is less than or equal to the end index. And then every loop, we need to check where the midpoint is. And the way we're finding the midpoint is we find the number of items past the starting index that the midpoint will occur. So items between start, end, and this is just going to be the end index minus the beginning index divided by 2. And we use math.floor, or we round down to make sure we're always getting a whole number. So end index minus start index divided by 2. And then the mid index is just equal to the start index plus the number of items past it. And now that we have our mid index, the first thing we always need to do is check if we found the target value. So if items of the mid index is equal to target, then we're done. We return early, we return this value, and we got our solution. If not, then what we need to do with our shifted search is now check which half is ordered correctly, and then use that half to determine which half the target must be in. So is left correctly ordered? And we know the left is correctly ordered when the midpoint is larger than the starting value. This means they're increasing the entire time. So items of the mid index, it's greater than or equal to items of the start index. If is left correctly ordered, well, now we need to check if our target is between the starting item and the ending item of the left half. So target in left half. So when the target is greater than or equal to the items at the start index, and less than the item at the mid index. And here we said greater than or equal, but they're all unique, so it should work out either way. If target is in left half, well, now we know we need to move left. So we bring our end index down to the midpoint. End index equals mid index minus 1. If it's not in the left half, then this means it's in the half with rotation, so we need to move our start index up past the midpoint. So start index equals mid index plus 1. And the reason we're doing mid index minus 1 and plus 1 is because we already checked the index up here. So we already know if that value was correct or not, so we don't have to check it again. And this is if the left half is ordered correctly. Now we can check if the right half is ordered correctly. So now we check right. So now we want to see if the target is in that correctly sorted half. So we say target in right half. And this is when the target is larger than the midpoint and smaller than the end. So target is greater than the item at the mid index, and it's less than or equal to the item at the end index. If the target is in the right half, it's in this correctly sorted half, then we need to move the start index up and eliminate all the items to the left. If it's not, if it's in the incorrectly ordered half, we just move our end index down. So end index equals mid index minus 1. And that's it. This is how we're going to hone in on that value, and we can return once we find that target and know what its index is. If we finish this loop and don't find the target, then we just return -1. Let's run our code. Small bug. Fix that. And they all passed. So we found the target in this shifted index in log n time by using a modified version of binary search. And we did so by checking that the half that is ordered correctly if the target is in between those values. And if it's not, then we go to the other half. And if it is, then we search in that correctly ordered half and then repeat this step every single time until we find the value. This is in contrast to a normal binary search where you only need to compare the midpoint to the target. But because it's shifted, we now use this range to find the value we're looking for. Thanks everyone, and I'll see you in the next lesson.